So first of all, I'm gonna introduce myself. I am the local neighborhood. What?
Nothing.
I'm the local. I'm your friendly neighborhood Theta Delta transfer Avali that happens to know how to design an integrated circuit or two. I have a website that you can go check out where you can find more details on the things that I've done in the past. But for now, we're gonna get started. This talk is called, I think, 3.5 years of open source silicon, a retrospective, and why you should care. But we're gonna go the other way around. Actually, it should actually be like why you should care and the retrospective. So we're gonna start with the why you should care part. So let me advance the slide. There we go. So I mainly make open source silicon. So I don't just make integrated circuits. I make open source integrated circuits. And so this whole thing actually kind of fits into the open source family tree as follows. You have the overall overarching nomica of free open source, which encompasses free open source software, free open source hardware, and a subset of that, free open source silicon, and that is where I'm the most active in that little subfield. The free stands for freedom, by the way, not $0. Keep going. So people like open source as a concept has a pretty long history, pretty much as long as computers have existed, because it simply turns out that people that have created something tend to want to share the thing that they've created. And so that means that as you go back in time to the first computers being built, as particularly home computers that people could have in their living room, you see people making these little programs that they think that are cool and then wanting to share them. And at the time, that usually meant sending them into like computer magazines and have them printed for people to type out on their computers. Or maybe using standard audio cassettes as a data carrier. So you write a neat little program, you play it onto an audio cassette, and you then copy that cassette at wherever. If you're a high schooler, you might bring your cassettes to school and have your friends copy them. So the idea of sharing software that you've made is pretty much as old as computers themselves.
Ah, yes, shareware.
Shareware.
No, that's what it's called, shareware. I love shareware. It's fun.
Yeah. Of course, nowadays it's been modernized a lot. We now have GitHub. So what you do is you go on GitHub and you find software of your choice, and you can view the source code there, and it's all online now, so you can access it at any time. But the fundamental idea of just sharing something that you've made has not changed. It's just become a lot easier thanks to the internet. And a lot of fundamental open source software that exists today exists because of the GNU project and the Free Software Foundation, which were founded around 1983. So that's how long ago this whole thing kind of took off. And thanks to these projects, we have things like
continue.
We have things like the GNU compiler collection, which is used in a lot of professional settings. Fun fact: the Free Software Foundation was founded because one guy had an issue with his printer that he couldn't fix because the source code for the drivers were proprietary, and so he couldn't fix it himself. So printers casually being so terrible, they spawn entire massive open source projects. It happens.
Printers.
No. And that highlights kind of one of the things that makes open source so important nowadays, is because it is programs you can download and install and run as a user, of course, but it's also software that you can modify, right? Because you have the source code, you can make changes to it. This was also a thing in the home computer days. People would publish mods to existing software or hacks that you could apply by typing stuff into the console, because everything was modifiable. And so, going back to the situation of the printer, if you had the source code for a piece of hardware that was more functioning, but you had the technical know-how to understand how to fix it, then you can edit that code to fix your issue yourself. yourself instead of having to wait on a software publisher to maybe one day publish a patch. And of course, a lot of people learn how to program like this because they find examples of software online that they can look at and maybe modify. I know that when I started learning how to program, I did it because I used MCP, which is a decompilation tool for Minecraft, so you could edit Minecraft source code. This was like back during the 1.2.5 days, I think. And that's how I started to learn Java, is because I wanted to modify things in the Minecraft source code. Of course, I did it horribly, and I had no idea what I was doing half the time. But it is a starting point, and that you can do at home. And that was kind of my entryway into everything that I do with computers nowadays. And I know there's tons of people who have gone from tinkering with open source software in their free time to be doing this actually as like a profession. So for the longest time, open source software was kind of more for curiosity than anything. But at some point, this commercial adoption started to happen, where open source software was being adopted increasingly by actual companies, software businesses, and also being contributed to by those professional entities. And as a result, we now have Linux and free open source software everywhere. In fact, I would be surprised if there's a single person in this room who has not interacted with a piece of open source software today. If you have an Android phone, that's Linux, so you're automatically doing that. If you're using Blender, or you're streaming or recording with OBS, those are examples of open source software. Or maybe there's entire programming languages that have open source compilers or interpreters, like Python or C. So you might be using a program that's proprietary software, but that uses something under the hood and is open source. So that's also a thing that could be happening. So this stuff is obviously really, really important. It's everywhere, which makes sense because we're talking about software that has had a lot of people, contribute to it. So if I go into the same repository from just now, Perl, which is just a utility found in most Linux distros, it has had a total of 1,200 people contribute some portion of code to it, and so you get sort of like you kind of get a piece of quality software out of that, because you have a lot of people working on this together, checking each other's walks, kind of making sure that the whole code base remains sane. Which is not true of many proprietary software projects. Ask me how I know. And of course, having the software be adaptable is not just good for individuals who want to fix their printers. It's also good for corporate IT teams. Maybe there's some feature that the business needs in a piece of software, but instead of having to wait for a proprietary publisher to add it after their support request, they can just modify a piece of open source software, add their own stuff to it that they need as a company to do their thing. So yeah, and of course this also leads to the creation of a lot of standards. So when you have a lot of people working together on one piece of software, or you have these different pieces of software worked on by the same people, then you often get the proliferation of standards, open standards between pieces of software. So you get a lot of interoperability that is unusually rare to come by these days. And of course, I know for a fact that the reason we use open source software at my workplace is probably because it makes us independent from a lot of third-party proprietary vendors. Yeah, I can't speak too much on that, but yeah. And also, if you have this many people at looking at your code, then that's basically just nothing else than a 24/7 security audit happening. Right? The code is out there in the open, anyone can look at it, and it means that anybody can find a vulnerability in it. And it turns out that the majority of people that find vulnerabilities in other people's code do the right thing of reporting it, or maybe even publishing a fix. Right? So at least for large open source projects, you get a kind of an enhanced level of security. Right, so next slide. Yeah. Exactly. And of course, transparency, right? If the source code is open, you know what's in it. That is always usually good. And there's this analogy of you bought a safe to keep all your valuables in, and that safe is of course protected by a lock, and it's supposed to be impossible for a thief to break in, right? So who do you trust more? The manufacturer that says, "Oh, we are not going to tell you what's actually in this lock. Just trust us; it's secure." Or the company that says, "Yeah, here's the schematics of how we built this. You can check yourself that it's secure." And yeah, there are certainly some arguments for both sides. Like you could say that just because a piece of software is open source doesn't mean a lot of people are actually looking at it and checking for security vulnerabilities. Yeah. But for at least really big projects like curl, you get a strong sense of security flowing. There's hundreds of people actively looking at it. Okay.
Actually,
yeah. Let me. Yeah. Going. Okay. So that's software, though, right? But software needs something else to work on as hardware. You have a physical machine sitting somewhere. And so this is a machine like that. This is just a really, really, really simple kind of thing. It's called an Arduino Uno. And these are really, really popular among makerspaces or people who are trying to learn. Like you'll find these in a lot of schools. And all it is there's a little microcontroller on there, and it's the big chip. That is just a tiny little 8-bit computer with a few kilobytes of ROM and a few kilobytes of RAM that can run simple programs on it. And it can use that to interact with other pieces of hardware that you can connect up to it on the headers on the sides. And so you can get like programmable hardware, sort of. It's an embedded device. That's what the name for that is. It's an embedded microcontroller. And the cool thing about this is that this is its schematic, and this is its PCB layout. Yeah, I can stay on the slides a little longer. Because this is an example of open source hardware, which means that on top of whatever software components come with this being open source, it also has all of the hardware schematics for it open source. So you can look at what's going on the actual circuit level with this device. You can even replicate this yourself. Like you can build one yourself. The only restriction is you can't use the official logos on your replicas of it, so that any like official productions can be identified by their trademark. But you can make one of these yourself. People have built these up on like breadboards. And of course, this is what I do a lot in my free time, is I make hardware. So this is just a small selection of the projects that I have completed. Image is flipped for some reason, but this is just a pile of stuff that I've completed. Now, there are a few of these that are clearly like hand soldered, like wired together on a perf board, but the majority of these projects printed circuit boards. So that's one of these things. So this is literally just a fiberglass pane with stripes of copper deposited and etched on top of it, and it just forms the interconnect. So that's all that a printed circuit board is. It's just the wires connecting parts. That's all it is. And then you put the parts on top of that, and they're connected as you want them. And this is usually very important because for a simple circuit, like you can see maybe in this image, it is easy enough to wire something up by hand with like individual wires. But as you get into modern devices, like your PC motherboard, for instance, where you have thousands of connections potentially, that becomes infeasible. And especially when you're doing mass production, right? You're not going to wire 100 of these boards up by hand, even a very simple circuit. You ideally want something you produce automatically, which is why these printed circuit boards are great. But the problem is that making these used to be not straightforward. So usually if you want a PCB professionally made, you go to an organization called a board house, or a company called a board house, which is essentially just a factory where they make PCBs professionally. And the situation, how it used to be over a decade ago, is if you were a hobbyist and you had a little PCB that you wanted to make, like this on screen, and you called up a board house, they would pick up the phone, you'd tell them, yeah, can you make me like 10 boards? And then they would laugh at you and hang up. Because at the time, the way the situation was is that you couldn't get PCBs unless you were a company trying to mass produce like thousands or tens of thousands of units and ready to pay, an equivalent amount of like tens of thousands of dollars up front. Small volume production wasn't really a thing for a really, really long time when it comes to, except at some point prices started going way down. I can now go onto JLC PCB, which is just my preferred board house, and I can upload them one of my layout design files, and they will quote me an amazing price. This is like for 5 boards, I think. So this is €1.80 for 5 boards. So it's low volume, cheap production. So how did it get here? Well, it's mostly because they changed the way they make these. The board houses realized that they can just put multiple of the PCBs from like different customers on one panel. So they make these PCBs in the shape of these like big ass panels, and then they take multiple customer orders and put them onto one panel, and at the last step of the production, they cut it, they slice it, and they sort it. So this kind of shares the area, it shares the cost, and it also means, of course they had to do some other stuff as well to get the prices down. I'm pretty sure they also had to change some of the ways about how they do things, how they do their tooling, how their machines operate. But the result of this is that you can now get very low volume production for very cheap, and this kind of led to an explosion in open source hardware. Because previously, if you wanted to make your own electronic circuits at home, you needed to know someone who knew how to make PCBs at home or do it yourself. Because you can DIY PCBs at home, it just requires a bunch of nasty chemicals that literally etch the copper on the PCB, so acids. You also need some photoresistant developer, I think. And it's like you have to handle a bunch of dangerous chemicals in order to make PCBs yourself. And so, yeah, you either knew someone who did this or you knew how to do it yourself, and it wasn't cheap, it wasn't easy, and you couldn't reach the level of production quality of these professional board houses. But yeah, that's what we have now. So nowadays, we have way more complicated open source hardware. So this is some open source single board computer I found. So again, this is something that's has all the design files available. And this is obviously a really complex PCB, professionally made, but we have those services now. And as a result, open source hardware is finally in a spot where it's slowly also entering the commercialization stage. So I think I have seen a Arduino type thing being deployed in an actual professional environment, but I'm not too sure. So it's happening slowly. It's still sort of in its beginning stages, I think. It's not as widespread as open source software, but open source hardware is kind of entering the same stage. And of course, it has the exact same benefits. Of course, open source hardware is a little bit different to get into because you need to physically make something, so you need money for the materials. And you need to, maybe if you're still hand assembling parts of it, you need patience and skill, but you can learn those things, right? It's an entryway. And of course, all the other things about safety and accessibility also apply. But there's one thing, right, about this, and that is that any board that you see, any piece of modern electronics that you see like this, has something in common. There's a particular type of component on pretty much all of them, and that is these integrated circuits, right? They're little black boxes that have something inside them. They're often described as the result of taking many circuit components and compressing them into a small area, and that's what makes it an integrated circuit. But really, what's going on inside it, right? Went backwards. Well, if you open one of them up, what you will see is this little plate of silicon that has components laying on top of it, or imprinted on top of it. So it doesn't look too dissimilar from a printed circuit board. right? So, but really, yeah. Here's another one. So this is from This is what is the Zepto bars. Should totally follow their little blog where they regularly post the result of opening up and imaging these integrated circuits. They're really pretty. And this is a rather simple one where you can still make out all the components by eye. But really, you can't make out too much. You can see that there's some wiring similar to the PC in that regard. But yeah. So says that then, yeah. Okay, so what can you do with these? Well, obviously you can buy a bunch of these chips. You can wire them up. They all have different functions. So there's like multiple chips in this video, but they all have a different function, and you can wire them up. You can use them to make stuff. This is not something I made. This is this is called electronic engineering, and that's what you can do. But what if you want to actually look inside one of these chips, or even better, make one yourself? Right? One of you think, I could figure this out. I could make one of these. Well, currently, if you pick up the phone and you call up a chip factory called a fab, they're called fabs. If you call up a fab and you tell them, hey, can you make a handful of chips for me, like 10 or 15, they will laugh at you and hang up. If you want to make chips, you have to be a big business that is willing to spend tens of thousands or even hundreds of thousands of dollars up front on a mass production. And, well, the only thing that's left to do is to try to make them at home. But that's of course not that easy. If making PCBs at home is hard, then making chips at home is like the final challenge of electronic engineering and like so many things. At home chemistry too, I guess. There is a person called Sam Zaloof who did figure it out. He successfully made a walking integrated circuit with a few transistors in his parents' garage, I think. And there's his website if you want to read about that. It is very fascinating, but I can't get too much into it in this talk. And yeah, unfortunately, trying to make integrated circuits at home requires you to work with a bunch of nasty chemicals. In fact, it requires you to work with the nastiest chemical. You need hydrofluoric acid to etch silicon dioxide. And if hydrofluoric acid is not just the clickbait video title strongest acid. It's also poisonous. It's a contact poison. It gets in your skin and it starts killing you. So if you accidentally get exposed to HF, it will kill you and then start dissolving your body. So not a great time. It is okay to work with in small concentrations. In fact, you can find whole household products with HF that have like 1 or 2% concentration. But in general, HF very dangerous. Yeah. Oops. Yeah. So that sucks. In fact, this you probably can't read this, but one of these days, I want to take a crack at it myself anyway. So I have some plans for this. Having multiple metal layers is an optional goal. I've been thinking about how to do this while not spending too much money, because this also requires a bunch of expensive equipment, like we're talking $10,000 expensive equipment. So it'll be a while until I get there, but one day this is on my bucket list, basically. I'll get to breathe in the chemicals.
I want a tholin computer.
But yeah, this sucks, right?
OS.
Be in the situation where the only way you can learn how to make integrated circuits is to go to university for it, and then hopefully get a job where they'll continue training you. And that's kind of suboptimal. It's also suboptimal for consumers because we're literally being sold black boxes. They're literally black boxes. They're shaped like that. That we don't know what's going on inside. And for the longest time, I guess that was okay. But the not having transparency on what goes on inside, say, processors is starting to bite us in the ass a little bit. I think everyone here knows the disaster with Spectra and Meltdown. So that is fun. We have bugs inside processors now. And actually the very first processor that Intel ever made, 8086, or the first one in the x86 series, 8086, had a hidden instruction in it that was not listed in any of the documentation or data sheets that on some systems could be used to circumvent the privilege privileged setup and access data that you're not supposed to. The very first 32-bit CPU that Intel made, i386, also had a secret instruction that could bypass privilege lockouts and access, and like bypass data access restrictions. So even when the CPUs are bug-free, they might have stuff in it that we don't want. And so this, again, the lock analogy, right, from earlier applies. But also just like this high entry barrier is like, it's annoying for me in particular because I really want to do this, because I'm looking like I really think that this is something that I could put at as making integrated circuits, right? So what do I do? Because this is what I was doing at in I think 2016 or 2017. Is I was making custom processors, just building them out of discrete logic functions. So almost every chip on this board implements just a single logic function, like an exclusive or an AND, and I'm chaining these together to make a processor at home. And I'm like, okay, hold on, I need some water. There has to be a better way. I keep forgetting to take care of myself and drink water.
Tholin, water redeem. Hail
How many
hydrate.
points is that? Okay.
Risk 5.
Or do I have stories to tell about Risk 5? Okay. Love Risk 5, though. We stand Risk 5 in this household. Anyway, also, like, if there's one thing that open source software has proven, is that that there's a ton of nerds on the internet, and if you give them the tools to build cool shit, they will make cool shit, okay? The nerds will build cool things for you if you let them. Let people make cool things, please. Okay, anyway,
excuse me. Tholin Unchained.
Yeah, this is my mind. This is my personal like gripe with the situation. There's so much cool invention that we're missing out on because they won't let us. I'm trying so hard not to swear. This is my own presentation. Can I swear?
No.
Thanks, Web.
Does that help?
Thanks, Web.
Someone swear. Now it's open swear season.
Yeah. So
Australia.
I allow you one fuck.
this is how it used to be for the longest time, right? For a really long time. Until one day, out of nowhere, Google, of all people, is like, what if we paid a fab to open source one of their process nodes? Because the way this works is you can't just design an integrated circuit and make it. Every fab has their own process nodes, their own way of making these things, with their own with their own physical stack-ups, their own methods, and you also have different sizes for things. That's what a like nanometer comes in, right? Essentially, you need information from the fab in order to start designing something that they can make. Right? You need tooling from the fab, you need data from the fab, you need information from them, and these tool sets, these process design kits, are often they are all proprietary, or at least up until this point. And so before you can even make a chip, a fab will ask you to sign a non-disclosure agreement and pay money up front just to access the things that you need to start working. And then they want money again for the manufacturing, right? And so even if you do that, even if you have the money to do that, whatever you make, you can't open source. Because either no one else is going to be able to open the files because they don't have the PDA, or maybe there's some part of the NDA that forbids you, right? So even if you had the money, even if you had the power to go to a fab and say, yeah, I can sign an NDA, I can get one of your PDAs, it doesn't matter. You still can't open source it, right? You still can't share what you're making. But this changed, I think, about 5 years ago, when Google walked up to Skywater Foundries and asked them to open source their 130 nanometer process design kit. This is an older process node. This is circa 2000 to 2001. So it is almost older than me, but it's something. And it's kind of like the first time ever that the general public got to look inside what actually goes on inside a process design kit, what's actually in there. And I will talk about that. And at the same time as this is happening, they also fund a startup company called eFabless. And what eFabless wants to do is make manufacturing of chips more accessible, right? By saying, well, we can put things on multi-project wafers, right? So similar to how the PCB board houses are combining multiple customer orders into one panel, we can combine multiple customer orders onto a single wafer and then split the cost. In the case of eFabless, they were doing 40 slots, right? They call these the actual manufacturing ones shuttles, and that's the term I'll be using. A shuttle is just one manufacturing run of a multi-project wafer, with customers being on the shuttle with their designs. And they were doing 40 seat shuttles, essentially, so the cost of manufacturing got split up 40 ways. And that's what that looks like before it's being cut apart. Yes, that's an Avali logo. I will get into that later. And so the final result was that cost went down for manufacturing from like hundreds of thousands of dollars to you could give eFabless $10,000 and a design, and it would come back to you with 100 chips. Of course, because they were splitting up the area of the wafer between customers, each customer also got less chips, right? Because the area, like the physical area, was being shared as well. So that's not too late. $10,000 for 100 parts is certainly better than the at least $400,000 of the full shuttle, right? If you do 10,000 times 40, you get 400,000. But that still implies, I think it costs like $100 per chip that you're getting back on a very ancient process node. However, it's definitely a start, and for the longest time, this is where people would go to make their at-home like DIY chips or chip designs taped out. Of course, at some point, someone thought, okay, but can we take this method even more to its extreme? So an organization called Tiny Tape Out is like, okay, what if we took one of those slots on the shuttle and we divided it even further up? And I think this is divided 100 more times, or 100 or 200 more times. So yeah, now you have even less area and you only get one chip back, but it only costs like $100, right? And now we're in the territory where if you're a hobbyist at home, you can get a custom chip made, right? You just need $100. I think it's a little bit more now, but around that ballpark, right? And this is all on one chip, by the way. They didn't cut this up further. They didn't slice this further. So if you participated in Tiny Tape Out, then when you got your chip back, and that chip wouldn't just contain the thing you made, but also the thing that 99 or 199 other people made. And so it was kind of like a group experience, kind of not just making something, but sharing it with all the other participants. And yeah. Anyway, by the way, this concludes the why you should care section of the presentation. So the next part of the presentation is a retrospective. And it's going to be a retrospective of my journey in particular. There's probably a lot of things that about the history of open source silicon that I'm going to unfortunately skip over because I didn't personally experience them. However, I want people here in the audience to get an idea of what it is that I actually do. Because I like to introduce myself to people as, a integrated circuit layout engineer, but I don't think a lot of people know what that actually means and what that entails. So that's what I want people to walk away with here, with the understanding of what it is that I do, while also giving a few notes about the history of open source silicon over the past 3.5 years since I got involved in this. Right. So I talked about Tiny Tape Out because that's where I had my start. Tiny Tape Out 2, which I think this is actually that chip, right? Tiny Tape Out 2 is where I got started, where I found this randomly while browsing the internet one day, and I decided, yeah, I can do that. I have 100 euros lying around. I ended up setting, exactly. So this is one of the things I made, right? This is
Tholin, you lost your mic. We can't hear you.
Ow. And now I lost my headphones too.
No.
I apologize. I get really excited about this stuff, don't I? This is some notes, right? Because back in the day, I was still thinking in terms of making things out of dedicated logic ICs, and so I did a lot of paper notes to figure out how to build things. So you can see me here walking out the instruction set for this 4-bit processor that I wanted to make. because if you look back at the chip, you will see that that's very little area. Like, you get very, very little area. There's a very limited amount of logic you can get into your dedicated little space. So I really had to be efficient with the way I built this to make it fit. Okay, but let's talk about what even is an integrated circuit, because I think that's what this is a good point to talk about then. So let's compare that for a moment to a printed circuit board. Let's start there. This is a really, really simple printed circuit board, and the way you actually make these designs is in a drawing software, essentially, because all you're doing is you're defining shapes of copper. Right? You're essentially saying, I want the copper here to have this shape to connect from this one place to another. And this is very obviously a vector drawing software, right? So this is vector graphics being used to define a physical shape that'll get manufactured. And you have multiple layers that you can draw on, right? Because if you look at this PCB, you can see it has copper not just on the top, it has connections not just at the top, but also on the bottom side of it. And so that's two layers. You also have vertical connections that drop through the board to connect the two sides. And those are called vias. That's another layer where those are. You can see there's some labeling. That's another layer. So you have all of these different layers that you can draw on, define this overall shape that is going to get manufactured. That's all you're doing, right? You're using vector graphics to define a shape, and that shape is going to get manufactured, and that shape happens to have a practical ability. It does something. Right. And integrated circuits are just that, but amped up to 11. So we have here's a little 3D render of a section of an integrated circuit, and you can see it is mostly metal connection. The majority of what you're seeing is just metal wires connecting different parts, and the transistors actually at the very bottom of this. So you can kind of think of an integrated circuit like an upside down printed circuit board. If you take a printed circuit board, which has like your PC motherboard, for instance, which has a bunch of components sitting on top, and you flip it upside down, what you get is a board that has components at the bottom and then a bunch of connections in a PCB above. And that's essentially what's going on in an integrated circuit. So the transistors themselves are actually embedded into the silicon that is... Did the stream stop? I think I accidentally canceled the stream. It's still going. Let me see.
We can see
Is
it.
the stream still going? Okay. Yeah, my overlay doesn't block like controller trigger clicks for some reason. I clicked on something in a video player. Yeah, so the actual transistors that are in an integrated circuit, at least on an older process node like 130 nanometer, are just they are like embedded into the silicon at the very bottom of the stack. So there's just a completely like perfectly flat rectangle of silicon at the bottom that the transistors are kind of embedded into. So I cannot get into the full details of this. This is actually a slide from a presentation that I did that completely explained MOS transistor theory in an intuitive way, but I'm gonna have to speedrun for this a little bit. So you have, at least on the modern integrated circuits, you have these devices called field effect transistors. And the way they walk is that you have this device that has three connections. It has a source and a drain, and it has a gate. Now the gate is not actually physically connected to anything. It is separated by a thin layer of isolation from the silicon underneath. And by default, you have the silicon that is filled with electrons or electron holes, just randomly. So the black ones are electron holes, and electron holes are just places where there's an electron but there isn't. And so the way they create this, by the way, is that silicon itself is actually neutral by default. So in order to get silicon to have an overall positive or negative charge, you intentionally introduce impurities into it. That's what's going on in this image. Right? The body, like the main part of the transistor, has been infused positively with impurities that make it positively charged. And then the source and drain terminals are the opposite. They are negatively charged. A different element has been used to infuse silicon. But what's important is that when a voltage is applied to the gate, as you can see here, then well, you get an electric field between the gate and the bottom of the chip or the body, and that's going to affect the particles in the silicon, right? Because all of the electrons in the chip or like in the silicon, they're gonna get attracted to gate because the gate is now charged, right? It's like magnets, but it's the electric field instead, but they can't get to the gate, right? The electrons, they really want to get to the gate and flow out of this material, but they can't because there's an insulator blocking them. So they just kind of line up at the top of the device. And, wherever you have a dense collection of charge carriers like electrons, you get electrical conduction, right? You essentially get a channel of conductive material forming between a source and drain, connecting them and allowing electricity to flow between the two. Because by default, the device is off. But by applying just a electric voltage to the gate, you can attract electrons in the material, which physically changes its properties and switches the transistor. So this is actually a physical process. Okay, and so actually making these looks like this. So this is in an actual layout editor. So whereas before, I scrolled again by exactly. Whereas before with this screenshot, this was in a editor software for PCs. If I go forward to this slide again, this is now a different kind of software that's meant for integrated circuits. So again, you can see that there's different layers that I can draw on, and I can draw metal, which is the blue stuff, draw transistors. I will actually get into that later, I think. But the idea is that I can draw transistors in the software by overlapping red, because the red is the layer where gates are formed. I can overlap that with the impurified doped silicon, and that forms transistors. So wherever you get a stripe of red overlay with an area of orange or green, that's where transistor forms. There's actually types of field effect transistors, depending on whether or not the underlying silicon is positively or negatively charged. Again, I will not get into this. Do not have the time. And then the blue is just metal. The blue is just metal. So this is usually can be aluminum, I think. Silver is also sometimes used, especially in modern process nodes. So it is a metal that connects things together. And then wherever you see crosses, those are vertical connections, which, yeah. Okay. Now, at the time when I started making things for Timetable, I didn't know about any of this, right? I was making things in a software called Logisim Evolution. So this is a very beautiful piece of software. This is the top level of my 4-bit CPU. But here's a small example of a circuit. This is a ring oscillator. So essentially what I'm doing is I am drawing up logic circuits by having these individual logical components. So for instance, there's two types of logic gates in here. There's an AND gate and there's an inverter. And each of these performs some simple Boolean function, like the AND gate, whose output is only on when both inputs are on. And this is what I was used to doing, because when I was building things like that processor I showed earlier, made out of individual ICs, I would build those things out of chips that would each only implement a simple logic function. And so I thought, yeah, okay, I can just take that same approach here, because this is actually done inside integrated circuits. This, what I showed here earlier from the editor screenshot, this is actually a single logic gate implemented in this. I think that's global. This is a different process node. This is not Skywater 130, but I'll get into that. But this is a single gate. It's an exclusive OR gate. You can see the inputs labeled A and B and the output labeled Y. And, because making something massively complex, let's say like Intel's modern CPU, out of individual transistors, like you'd be sitting there for years just trying to get started. So a much better idea is it circuits that implement logic functions, and then instead of making individual transistors, you can place these macro functions and just wire them up. So you have all kinds of different cells for different logic functions. And this is called a standard cell library. What's even better is you don't have to do this by hand, right? You'd think that after making these logic schematics like I am, my next step would have been to try and place down in a layout editor and wire them up together, but this is not true. we use a piece of software called a flow, which is just a collection of programs that attempt to automate the process of actually generating the layout, the physical chip layout. It takes in, or at least at the stage where I was starting, it takes in a netlist, so a circuit schematic of logic blocks like this one. It translates those into logic blocks I found in the PDA, and then it does two things: place and route. The first thing it does is it tries to figure out an optimal placement for these cells, because if you have two logic gates that are connected to each other, you don't want them on opposite sides of the chip. You want things to be close together that are related to. So that's a bit of a puzzle for the program to solve. What's even more of a puzzle is routing, which is when you actually draw up all of the connections between these different cells. That can often take a really long time to run. But this is something that can be automated. So this layout, what you're looking at right now, was not made by a human. It was made by a set of computer programs that took in a logic netlist of logic gates and then automatically transformed it into a chip layout. And this is how a lot of integrated circuit layout engineering is done these days, because it's a lot more efficient. Like, yes, you could theoretically probably make something more optimized by drawing up each individual transistor by hand, but that would take too long, right? So it's best to choose this median approach of letting the computer handle it for you. Okay. And so I get my tiny tape out 2 chips back, and they do walk. So this is me demonstrating another thing that I take out on this tiny tape out 2 chip. I actually had 6 submissions on there, which is, I think, still the record for most submissions by a single person to tiny tape out. The first was that 4-bit CPU that you've seen, and it's just barely capable enough to render the Mandelbrot set, which I'm very proud of. That was my goal. This next one that you're seeing here, get the video to restart, yes. This next one here is, it just counts up on a set of 7-segment displays and has a multiplexer displays. So it's actually only showing one number at a time, but it's going through them so fast that it's like how video fakes motion on the human eye. Just going really fast. Similar. It's actually only showing one number at a time, but you can't tell, it's too fast. I also made this, which is a retro sound generator, like you would have found in very old computers. This thing has 2 square wave voices, 1 triangle voice, 1 noise voice, but it ended up not working. This thing was completely dead on arrival, and there's another presentation I did a while ago called How Not to Design an Integrated Circuit that I will, for people do at the end who want to find out more about all the times that I fucked up. But, this method that I was using of defining my logic in a circuit editor like this is actually not how people do it. In fact, I had to figure out myself how to coerce these schematics into the tools or into the flow that Tiny Tapeout was using, because the software I'm using for this Logisym Evolution was not meant for this. It was not meant to be used to define integrated circuit layouts, right, or schematics. So instead, what people do is they use something called Verilog or some other kind of hardware description language. So this is like a programming language, but instead of writing a program that is executed by the CPU, describe what you want a circuit to. And then a tool called a synthesizer will come that code and turn it into logic circuits, which goes into the rest of the flow to be turned into a chip. So that's a little bit complicated to wrap your head around, especially if you're used to programming in an actual programming language, because you have this example here, right, where you have a counter variable that gets incremented regularly, and then an LED gets toggled when the counter overflows. But there's some really weird things going on here, like the counter being a 24-bit value, or the fact that this function seemingly gets called by a signal. If you've ever done anything with protoflux in Resonite, then this will actually be intuitive to you eventually. But yeah, there's a signal coming into the circuit that triggers something to happen, and yeah. And of course, there's a lot of parallelism going on, right? It's not like a program where you run one line of code and you do the next line of code and you do the next line of code. Because you're defining hardware in these languages, everything is happening at once. Right? Every statement that you write is kind of computing in parallel, and that can often be very confusing for people who come over from programming. Which is exactly why I was using non-system evolution, because I wanted to get my stuff done before the deadline for Tiny Tape Out, and learning this was a little difficult, right? Still, I ended up making one submission to Tiny Tape Out with Verilog, a rudimentary understanding of it, which is a thing that just rolls a number on a 7-segment display like a die. Oh, right, I also made this, which is there's a circuit on that chip that does nothing but print messages on a LCD display. So that the messages themselves, like the actual text, is baked into the chip as well. So it'll always do the same thing, always print the same text onto a display. There's some other screens it displays, but this is one of them. Okay. On. Yeah. Okay. So at this point, Google's like, why not keep going? And so on top of the Skywater Foundry's 130 nanometer being open source, we also get Global Foundry's 180 nanometers. And I think this one might actually be older than me. It depends on when exactly this variant of it released. It might be early 2000 or 99. I couldn't find any concrete info on it, but this one might actually be older than me. But we now have 2 PDKs, and the way they decide to celebrate this release is by doing an open shuttle on it. So eFabless and Google at the time were running a program called OpenMPW, because usually you have to pay like $10,000, right, to get put onto a shuttle, but that's a lot of money, and they wanted to encourage people to get started with these open source PDKs. So in parallel to each open shuttle, each paid shuttle, which ran once every 6 months, they would run an open shuttle, which was one where participation was free. Which you could just send in something, and would be put on the shuttle, and you could get free chips made. Like, there's no strings attached; you just get free silicon. Of course, whenever there's free stuff, a lot of people want it, so there was often more applicants than the 40 slots would allow. So they used the lottery system to determine which submissions would make it onto the 40 slots of the free shuttle. And this shuttle is where this shuttle that they were doing with 180 nanometers, called GFMPW0, is my first experience actually making a full chip on my own. Well, sort of, asterisk. And so that's what I did. I decided to make another 8-bit processor. And this is a CPU on there that is inspired by something called the Signetics 2650, which is an 8-bit CPU from the 1970s that was abandoned shortly after its release by Signetics. And I had a couple of those original chips laying around, and I was like, this thing is actually cool. I have a picture of it here. No. This thing is actually pretty cool, so why don't I try and replicate this design on this process node and tape that out? Have that be the thing that I tape out. And that's what I did. So if you look at the picture on the right, and you see like at the top center that block, that's what I taped out. The rest of this that you see was a wrapper provided by eFabless, so that's not my work. Only the like little rectangle there is. And that contains a little 8-bit CPU that I decided to make. And this also starts a trend of me taping out like replicas of retro stuff, like retro configuring stuff. But yeah, we'll get to that. So here's me trying to bring it up. I made this little PCB that I could put the CPU on, and it had some RAM and some I/O. Has an old style RS-232 serial port for communication, and I could use this to poke at the CPU and run programs on it. I'm gonna need some water again, hold on. one of the things you have to know about the CPU is that it was so broken. It couldn't even add or subtract numbers properly. That's how like broken it was. It had so many bugs in it because I rushed the design in like 2 weeks and I didn't know what I was doing. I'm pretty sure this is like one of the worst chips ever taped down. It's so bad. Yet somehow I persevered and I fought through all of the issues. I found workarounds and fixes in software or hardware for all of the shortcomings that this thing had, which is like a really long list. Again, go watch the other presentation after this. And in the end, I actually managed to coax this thing into running one of my electronic con badges. So I took this with me to Eurofurence a couple years ago, and it has my custom like little CPU on it, and a little bit of RAM, and has a screen. And despite this CPU being like the most glitched thing on earth, I got it to work. I got it to run. It even renders an Avali at the end. And this kind of also plays into a trend of free open source silicon, like FOSSIC people accomplishing the impossible. Like it has happened multiple times now that we've had people who are actually in the semiconductor industry professionally come up to us with a problem that we're having and be like, yeah, this is impossible, you can't do this. Like, I'm pretty sure people told me, well, our IP, that CPU, gotta trash them when I, talked about this thing having, like, a broken adder. And, I got it to work anyway, fine. Now, I accomplished this, what I was told was impossible, and this keeps happening for some reason. Like, on the very early fabless OpenMPW shuttles, the chips that people got back, like especially on MPW-1, I think, were like ultra broken, and people got them to work anyway, despite the fact that people were telling them that they're attempting an impossible task. I think I wasn't there for that, so I'm kind of just paraphrasing from what other people have told me. But yeah, seemingly we must be doing something right if we keep accomplishing things that people say are impossible. And if I let this video play for another few seconds, then we're gonna get the rendered Avali, I think. I'll just let it play. Yeah, it's very low resolution. The screen is like 128 by 60 pixels, but it is indeed rendering an Avali. Alright, get some water.
Bird.
That's pretty good for like a hopelessly broken CPU, isn't it?
Bird.
Okay. Unfortunately, this shuttle where I got to tape out this really broken CPU was also one of the last OpenMPW shuttles. Google, in their infinite wisdom as usual, decided to just completely kill the program and stop funding. So, I guess add that to the killed by Google graveyard, right? Yeah, so no more free silicon. So that's the point where I was like, oh my god, it's so over. Especially since I thought I would forever have this broken processor running and weighing on my conscience, because I will never get an opportunity to fix it unless I can get $10,000 from somewhere. However, with that announcement of the shuttle or the OpenMPW program being officially discontinued, came the announcement it will be one last shuttle, GFMPW-1, again with the GlobalFoundries 180 nanometer. Right, because you have to imagine what happened here is that there was months of no news about OpenMPW and no new shuttles running, and then suddenly, by the time that we all knew that it was dead, was when the announcement came and the thing about GFMPW-1. Right, so this was going to be the last ever one of those free shuttles, and I decided to lock in. I don't think I've ever locked in so much in my entire life than my submissions GFMPW-1. So what you're looking at right now is not just a fixed version of that 8-bit CPU. I turned it into a full-fledged microcontroller. Yes, it has a little bit of RAM on the die, it has GIO ports, it has timers, it has serial ports. I put a Commodore 64 SID on there just because I could. And of course the Avali logo in the corner. And I really locked in on this. But however, I somehow finished this under time. Because this time the deadline was 5 weeks into the future, so I had a little bit more time than the 2 weeks before. I somehow finished all of that in like 3 weeks. So I still had time, and so I decided that I was gonna do another submission. Oh right, first of all, really pretty photographs that someone took. Yeah, of the Avali logo. I'm just being like unapologetically Avali-Therian on main in the Silicon community. Or at least as far as I can, and it's great. So I decided that I was going to make a second submission. I was going to tape out a second chip layout to the same shuttle. Because, technically speaking, there was nothing in the rule about submitting two things to one of the open shuttles. So I just did it. And somehow, despite the odds only being like 25%, both got accepted. So, yay. I was very lucky for once in my life. And this chip is a multi-project die. So this is when I got the idea, well, why don't I, if I have multiple ideas for things I want to tape out, why don't I put those multiple things in one die and then have a multiplexer, like a special structure on the chip that switches which of those multiple things is active and has access to the physical pins of the chip. And I came up with a framework for this, and this framework is actually still something I use to this day. Like my latest tape out, I was using the same framework again to put multiple things onto one die. But there's multiple things on this one. I decided to challenge myself and see how fast I can design a microprocessor with a custom instruction set from scratch, including verification test cases. It turns out it only takes me about 9 hours to do that for 8-bit RISC CPU. And I call it a QCP. It has surprisingly few bugs. I taped out a replica of a 1-bit CPU, MC14500. Yes, that's a thing. That's a thing about it on my website. I also decided to tape out a custom RISC-V core that I made entirely from scratch. It only had the I and M extensions, if that means anything. And it required external memory. It had like a 16-bit address data bus. Yeah. And that also worked. A person called Regunity wanted to tape out some stuff, so I told him, yeah, just throw me the stuff, I'll put it on my multi-project die, I still have space. So I think there's 2 designs on there that are actually not from me, but by someone else. So I can't talk much about them. I don't think they've even tested them yet. Or at least I haven't heard back from them yet. Whatever, they have the chips, so. And I decided to also tape out some stuff from Tiny Tape Out 2 again. Like the completely broken sound chip from Tiny Tape Out 2, I put that on here and fixed it. Unfortunately, I'm not a musician. I don't know anything about music, so I have this perfectly working custom sound chip and no music to play on it, because like I'm not a composer. I really should have thought that one through, but I didn't. I also taped out a replica of the famous PD1140, but it ended up having some differences to the original instruction set. It's still perfectly fine in working 16-bit CPU, however. It's just different. And I taped out a Commodore 64 SID replica, if that means anything to anyone here. Which also mostly... Okay. Here's some of the PCBs I made, because when I get these chips back, I have to test them. This is called bring up. It's the very first time you power up one of those chips, you throw electrons into it and you test it. It's called a bring up. And I decided to make a bunch of different boards for this. Some made by hand, some PCBs. The bottom right one is the EP1140 replica. There's like the full miniature front panel, the lights and switches. Yeah. The RISC-V board is at the bottom left, but I'll talk about that in a moment. Okay, and of course, I also ran out of simulations, right? Because the previous tape out, the 8-bit processor that was really broken, it was that broken because I decided to cheap out on simulating it, because that's a thing you can do, right? Once you have your chip design built, you can throw it at a simulator, at various kinds of simulators. You can run just a software simulation of how it performs, what it does, and you can use that to test its various functions. And when you run one of the simulators, what you get out is, fun little oscilloscope traces like this. And usually the way this goes is you write something called a test bench, which is a piece of software that automatically supplies inputs to the chip, the simulator chip, and then checks if the outputs it gets back are correct. And so the testing is fully automated. I don't actually have to look at these oscilloscope traces unless something's going wrong and I have to debug it. For the most part, it runs all these traces automatically. And that's also why the second version of that 8-bit CPU ended up working flawlessly with basically no bugs that I found so far, because I made an extensive list of test cases just checking everything. Okay.
Nice.
So at some point, I forgot when exactly, a fab here in Germany open sourced their one of their PTKs, 140 nanometer by CMOS one, but not because of Google, but because of government funding. I think there was some German government project, but I don't know too much about it. I've never taped out with it because making full chips with it on your own is not really accessible. You can get it, you can access it through Tiny Tape Out though. But again, yeah.
Are you keeping track of the schedule at the moment as well?
Yeah, no problem. I think so, at least.
Okay.
I started a bit late, unfortunately, so things will get shoved around.
Yeah.
But it shouldn't be a problem.
It's at closing last jump time. It's about another half an hour until Tycho's one, just so you know.
Got it. So unfortunately at this point I'm in it's so over mode because, no more open MPW, I don't have money. And Google as a whole appears to be slowly exiting open source silicon. So at this point, one more tape out opportunity presents itself when Unity and some other people come up to me and are talking to me and like, hey, can we use your multi-project framework to tape out something, because I want to make some retro replicas. And so I decided, yeah, sure. And they let me use the leftover space on the die for my own things. So again, it's another multi-project die with many things on it. I'm going to rush through a few things here. This has a Z80, 6502, 1802, 8X305, which if anybody here knows the 8X305, oh my god. I had a replica of it ready anyway, for some reason. You know that board I showed at the beginning where I tried to make a processor out of individual logic chips? I decided to tape that out on an integrated circuit to kind of come full circle. And I also taped out the Itanium at home that I was talking about yesterday, and my VLIW CPU. That's actually most of the die area. If you look at this photo and you look at the top half of that, that is the VLIW. All of that is the VLIW. Okay, but of course, that's just like a one-time thing. So again, it's so over again, the JPEG, and then even worse, eFabless, like the whole company eFabless goes under, right? So even if I had $10,000, I couldn't tape out anymore because eFabless is kill. So again, add that to the Google graveyard. So now it's even more over. I do take tape out opportunities where I can take them. So this is on the minimal fab PK, which I won't get into too much. I don't think this ever got manufactured, even though I submitted it to their little competition that they did. I actually won a prize for this, and it's really, really pretty. And you can actually find this in my room on the ship in like a frame. Okay, I'm hanging up. Well, so is this it, right? Tiny Tape Out is looking somewhat okay because they've Tiny Tape Out at this point is operating at a scale where they can start directly communicating with fabs. But of course, with Tiny Tape Out, you have certain restrictions on I/O and area. IHP still offers a multi-project wafer program, but it has some limitations and is really expensive. Cadence begins offering Sky 130 shuttles, but we haven't even seen any of those back yet. And I think that was like a year ago. But luckily, whenever there's an it's so over phase, we also eventually get into the we're so back phase. So that was kind of the, I think, middle of 2025, middle to end of 2025, where we get these companies popping back up. Chip Foundry is supposed to take over where eFabless left off. They offer fabrication services with Sky 130 nanometer, but it's now at an increased price of $15,000 per 100 chips. So most likely it appears that eFabless was actually selling at a loss before, which is not too surprising, honestly. And now it's actually more expensive. However, there is one of the people affected by the whole Fabless shutdown and just holding out of open source silicon was Tim Ansell, someone who used to work at Google and I think helped coordinate these open shuttles. And he decided that he was gonna do it himself, right? He was doing the fine, I'll do it myself meme, right? And decided to step away from Google to found wafer.space, which is another one of those services where you can tape out your chips, this time on the Global Foundries 180 nanometer PDA, and but at a much better pricing, right? They offer manufacturing services at a price point of $7 per die for 1,000 dies. That's a total of $7,000. But instead of getting 100 parts, you get 1,000. So it's both cheaper and you get more stuff. Right? That's really important. If you're willing to accept that only having half of the total area, you can go even cheaper. So this is now beginning to enter the range where I can afford it. That's great. Right, very hype. However, I got onto their first shuttle for free because of all the work I've been doing getting the PDA. Oh, whoa. This is not supposed to be that. Okay. Yeah, anyway, just because I make a lot of cool shit, right? If you make cool shit, right, good things happen. This is the total combination of designs for their G801 shuttle. The question marks are ones where it was those are designs for that were not open source, right? Because you can tape out proprietary things on these services, right? It's just you can also tape out open source. That's important. And I decided to tape out this. And this is where my computer actually starts lagging because this image is such a high resolution. So this doesn't just have a bunch of stuff on it, it also has art on it, because I decided why not? Why not be even more Avali on main? So we have art. I'm gonna showcase this, right? We have art from Darcy, who is up there. Hi, hello. So this bird up there made art of me, and it's now eternally on this chip. There's also these two, which were made by Luna Midnight, who I don't think I see in the crowd. Who went above and beyond, because the thing is with because you're drawing in a metal layer, there either is metal or there isn't metal. You don't get color depth. You get on or off, right? How do you do shading when you only have black and white? And somehow Luna did that. I don't know. It's magic to me. I'm not an artist, so. And of course some logos as well. Yeah, and the one on the right was made by Ember. I think that's supposed to be the logo for the Avali Expeditionary Fleet. And I just put it on there. Yeah, okay. I was gonna go into a little more detail, but I'll speed through it. There's a bunch of VA demos. There's some stuff from Timetable 2 again. There's I replicas of more retro stuff. There's an HP Nano processor. There's a simple 8-bit CPU that I copied from Minecraft. Long story. There's replicas of the 6502 and 6510 that are exactly identical to the original MOS chips, including the undocumented instructions, which I think nobody has done before. Nobody has produced a chip that's a perfect replica of those chips, which I think the retro computing people are going to find that very exciting. There's a SID. Again, there's a dual SID actually. There's something that I call the SID 2, which is the SID but with more waveform options and FM synthesis, but it's fully backwards compatible with the SID. There's a replica of the C64 PLA, more retro stuff. There's stuff for homebrew computer builders. There's a GPIO chip that has a bunch of GPIO on it. There's a DRAM controller for retro DRAM. There's my RISC-V CPU again, except this time it also has the atomic instruction set. There's an NTSC video generator test, and that's so large because I put a whole bitmap image in there. When you activate that one and you connect it up to a TV, it displays Darcy's art. Yeah, again, this must be a personal record for a number of things I put onto a single chip. Holy crap! Don't worry about the one that says redacted, by the way. Just don't worry about that one. Okay. This is the clearest photo I've managed to obtain so far, what that die looks like. Unfortunately, a lot of the art is unrecognizable because the individual like lines are so thin that they can't be picked up by the camera. But you can see it's there. Yeah. Let's see. Yeah, and I've also been getting into manual layout because up until this point, I've been using these flows to automatically build code into layouts. But now I am starting to actually make the layouts by hand, like actually draw up things on a transistor level. So this is actually a thing that I made. This is a D flip-flop, so this is like a single bit memory, and these are user registers and such inside these lines. And I made this one. I made this layout, and it is a standard cell, so it is meant to be used in a flow, but the standard cell was also made by me. In fact, I made an entire standard cell library from scratch on Sky 130, and then I made another one on GF 180, which has been insanely helpful so far, I think, because mine works properly at 3.3 volts. Long story, again, I don't have time, but yeah, that was a lot of work. This is a thing that I taped out on a die I showed earlier. With G1801. So this is a digital to analog converter. So this takes in a digital value and it outputs a analog voltage that is proportional to the digital value. So this is how you get simple analog output. And yeah, I'm zooming in because most of it is just this big fuck you transistor to push giant currents, by which I mean like enough for 1 kilo ohm load. And yeah, there you can see the actual digital to analog converters at the top, and then there you can see a bunch of transistors. This looks different in a standard cell because there's different design methodology doing analog. Again, can't get into it. And then to actually make these, right, there's several pieces of software that I use. I did want to explain what it is that I do. So making something analog starts with capturing the schematic of what you want to make in something called XSchem. So this is an ancient piece of software that's older than me. It has some strange controls, but it's relatively easy to get used to. And you can see here, this is a schematic layout for an operational amplifier, which is a component of that converter. Here's what it looks. Here's the full schematic for that digital to analog converter. This previous thing here is the little triangle symbol on the right here, and this is a resistor ladder. So this is just a giant voltage divider where each stage contributes half as much voltage as the previous one. And so the output of this huge chain of resistors is a voltage that's proportional to the digital value going into the thing, but it's really weak, it has a low current. So I'm using an amplifier at the right to boost it. And that's what takes up most of the area. And then of course I want to make sure it works. The cool thing is XSchem fully integrates ngSpice, with ngSpice being a popular tool for simulating electronic circuits. And you can see I'm using that here to run a simulation and inspect the results live. Now you can see there's some strong transient spikes coming out of the resistor ladder inside the circuit, but the amplifier smooths it over mostly, and so the output looks clean for the most part. Yeah, and then of course to actually make the physical layout, I then open up a software called Magic. So this is Magic. Magic is a software that I think was originally released in 1983, so way older than me. And this is what it looks like when you start out. When you first start a new project in Magic and you throw a schematic at it that you've done, it just instantiates all of the transistors and resistors and stuff that you've defined in the schematic. And now it is your job to properly lay them out and connect them together. And that's what it looks like in the end, right? After a lot of work. Actually, you had to read this like 3 times. I kept doing it wrong. But of course, if you're doing something on the transistor level for standard cell logic, I often skip XSchem and I just do it. I just make the circuits. I know it just makes sense in my head. I can do these without thinking too much about it. These for simple logic functions. Yeah, and so the thing about Magic is, this is actually not all of Magic. This is all of Magic. This is the console, right? Because the way you operate the software is by typing in console commands. Now, there are some keyboard shortcuts, and the keyboard shortcuts would make Blender blush, let me tell you. And there's some mouse controls, but like this software is so old, it does not support like click and drag. It only detects left clicks and right clicks. and scroll wheel like shifts, and that's it. And you can't click and drag. There's no functionality for that. But you know, you're also supposed to be able to do anything that you move the mouse with the console in case you don't have a mouse. At least I think so. And so a lot of editing in Magic actually means making a selection with the left click and right click in the editor, and then typing in console commands to modify the layout. Or you can get into the weeds of defining your own hotkeys, because this is a scriptable program, and you can like make scripts and you can bind them to keys and you can accelerate your workflow like that. But I never got too into that. There's another piece of software that exists called K-Layout, but that one doesn't have as many of the critical features as Magic, I believe. But this is K-Layout, right? I've only used it once for that minimal fab takeout. Right, so Magic is really trying hard to pretend that it's a raster graphics editor. Like, remember, you're defining vector graphics when you're making these chips. Same as PCB. You're defining vectorized shapes, right? You're defining geometric shapes. And Magic, however, tries to pretend that it's a raster editor. So whenever you make changes in a Magic layout, it's like changing pixels in an image, and then it tries to convert that into rectangles in a vector graphics file. Meanwhile, K-Layout is a proper vector graphics editor, so you can define arbitrary polygons. You can basically like that. Maybe Magic can do this. I haven't figured it out. But the way Magic is intended to be, seemingly, is that everything's a rectangle, and it's trying to be a raster editor. But that's K-Layout. This is more like a vector graphics workflow. Yeah, and so what next for me personally, as well as open source silicon? Well, for me, making chips is never the end in of itself, right? I make chips because of the things that I can think I can do with those chips, not because, oh hey, I've made a chip that's cool, that was my goal, right? And so, for instance, here you're seeing me use the second version of that 8-bit CPU. I made this little board that's like an Arduino, and I can have this on my breadboard, and I can use it for like stuff like a microcontroller. So I'm actually using these chips in projects. This is another Eurofurnace badge I made that has my VLIW CPU on it. Another project. Here, I took the RISC-V CPU I taped out during GFMPW0, I programmed it with a software network stack, and it connects to the internet. I think I'm the first person ever to connect their open source silicon to the internet. I'm not entirely sure. But there you go. I can do that. And I ended up also programming it. A HTTP web server is serving a simple website. So, yeah, I'm doing stuff with these chips, right? And I will keep doing things. Especially as I get more and more of them, and I have more of a set of these chips that I can pull from for the functions. I'm also trying to get deeper into analog, so this is me trying to make an NTSC video signal generator. Particularly the color component is really difficult, so that's part of generating the color signal in NTSC. Yeah, I'm also working on a really amazing but very secret project I'm not ready to talk about yet. That will hopefully also be worth a presentation when it's done. Maybe not necessarily at AvaliCon, but still. And yeah, more wafer.space shuttles are definitely coming, I think, at this point, which is good. Wafer.space is also aiming to open source more modern PDKs from Go Foundries. I think the next target is 90 nanometers, I forgot. And of course, we are now finally at a stage where open source silicon has a chance to enter like commercial production or commercial use. Remember, you can get chips taped out at wafer.space for like $4 a die. That's like cheap enough that you can start making products of them. In fact, that's the thing I want to try doing. Right? It's making actual products I can sell with my custom chips that I taped out with wafer.space, which would be a first, I think. So we're finally entering that stage of open source silicon. And of course, more cool shit, right? I'm a nerd, and there are other people that are nerds. We're gonna make cool shit. Like, I've been skipping over so much cool shit, like people taping out entire FPGAs and like multi-core processor, what are they called? SoCs on these process nodes, which, by the way, is pushing these process nodes way beyond their like 2001 limits, right? And of course, continuing to heavily rely on other open projects. So, for instance, RISC-V gets a lot of attention in the silicon community. because it's an open CPU architecture that anyone can implement. I think that's ultimately also going to be beneficial for both sides of that, for instance. Yeah, and I guess lastly, if I kind of want to encourage people to also go down this road, because I think it's really cool and you can make some awesome stuff. And especially if you're already an electronic engineer, but really getting into these things is really easy. Tiny tape out is very cheap. You don't even need to, I think, you don't even need to be an electronic engineer anymore to engage in it. When you get something from Tiny Tape Out, they send you back a board of the chip on it, and you can plug it into your PC and you can play around with it just over USB. Getting into electronic engineering is constantly getting cheaper thanks to open source projects like Arduino. And of course, one of the things that maybe is a goal for Wafer.space is providing more free silicon opportunities for people in place of the OpenMPW program. Rest in peace. So here's some resources. You can go to tinytapeout.com, figure out how to do that. Again, it's really easy. They even they have a web editor. You can make your designs entirely in the web, either in Verilog or actually drawing up the logic schematics like I have. So you can do the whole process of integrated circuit layout engineering without leaving your web browser, which I think is cool. Wafer.space, of course, they're running a shuttle right now. And me, if you're someone from AvaliCon and you want to get into these things, you can talk to me and talk to me for advice. Okay. I need to jump the ship, right? We need to do the thing. There's 10,000 other things I want to talk about, and probably the end of this presentation is really jumbled as a result of that. But I'm literally out of time. So, thank you.
Yay! Nibble the bird.
Yay!
I'm gonna drink so much water.
Recording stopping.
Hey,
I need to
Tholin, check your
do a sound
Wow.
effect for clapping, so that way I'm not just.
Where?
Oh.